In 1995, a Swiss astronomer named Michel Mayor sat at an observatory in southern France and detected an object orbiting a star named 51 Pegasi. The object had an orbital period of 4.23 days. This number meant something that violated every model planetary scientists had constructed over 2 centuries. A planet this massive, this gas giant comparable to Jupiter, should not exist this close to its host star. The orbital mechanics were impossible. The temperature would be 607 degrees Fahrenheit. No planet should survive at that temperature and distance. Yet it was there. The signal was unmistakable, confirmed and published and celebrated as the first exoplanet ever discovered. What the scientific community did not know in 1995 was that this single discovery would fundamentally reshape astronomy, would trigger the funding of thousands of exoplanet searches, would make visible the fact that planetary systems were radically different from what the solar system implied, and would directly cause the eventual discovery of 15 planets that were then so comprehensively lost to follow-up observation and institutional memory that today, 3 decades later, they have effectively vanished from the astronomical record as if they had never existed at all. The discovery of 51 Pegasi b in 1995 was the breaking of a dam that had held for 400 years. Since the invention of the telescope, scientists had assumed that if planets existed around other stars, they would resemble the planets of our solar system. Small, rocky planets close to the star, massive gas giants far away in the cold outer regions, a stable, orderly arrangement that reflected the cooling process that formed our own solar system. The discovery that this was completely wrong, that the universe did not care about human assumptions, about planetary arrangement, triggered an explosion of observational programs, grant money flowing into exoplanet research, and most importantly, the lowering of publication standards. Within 5 years of 51 Pegasi b's discovery, exoplanet detections were being announced almost weekly. Some were real. Some were instrumental noise, misinterpreted as planetary signals. Some were methodological artifacts that disappeared when more careful analysis was applied. But the excitement was so overwhelming that the distinction between confident detection and preliminary candidate began to blur in ways that would have dramatic consequences decades later. The specific reason why 15 planets from this early exoplanet era were comprehensively lost has to do with something that nobody in 1995 anticipated. It was the shift from ground-based observation to space-based observation, and more specifically, the arrival of new instruments that made the old detection methods obsolete almost overnight. The transit method, which measures the slight dimming of a star's light when a planet passes in front of it, became the dominant exoplanet detection technique in the 2010s, displacing the radial velocity method that had discovered the original planets. But the planets discovered by radial velocity were discovered on stars that had never been systematically observed by transit instruments. They were orphaned. They were never followed up. They were never confirmed with the new methodology. And then something worse happened. The researchers who had discovered them retired. Their data went into archives. The institutions that had supported the observations lost funding. The original papers were rarely cited, and within 2 decades, these planets had simply ceased to exist in any meaningful way in the working memory of the astronomical community. The technical dimension of these lost planets is what makes their disappearance comprehensible. The radial velocity method works by measuring the wobble a planet induces in its host star as it orbits. The star moves slightly toward Earth, then slightly away from Earth, in a repetitive pattern. This creates a Doppler shift in the star's light. By measuring this shift with a spectrograph attached to a ground-based telescope, an astronomer can infer the presence of an orbiting body. The technique is sound. It has been used to discover over 1,000 exoplanets, but it has a critical limitation. It measures the minimum mass of an orbiting body, not the actual mass. It also requires multiple measurements over many years to establish a genuine signal rather than noise. A planet with a long orbital period might require 5 years of observation to establish its presence with statistical confidence. Many of the planets discovered in the 1990s and early 2000s were detected with modest signal-to-noise ratios. They were real in the sense that they were genuine detections of real gravitational effects, but they had large uncertainty margins. They were candidates more than confirmations. When new instruments arrived that could have confirmed them, the original observers had moved on to other projects. The stars were not observed with the new methods. The candidates faded from the literature. The human dimension is where this story becomes genuinely tragic. Consider the case of the planet orbiting the star Tau Ceti, discovered in 1998 by a team led by Geoffrey Marcy at UC Berkeley. Marcy was one of the titans of early exoplanet astronomy. He had discovered dozens of planets through dogged observation and technical innovation. The Tau Ceti planet was announced with significant fanfare. It was published in a respected journal. It appeared in press releases. Astronomers around the world added it to their databases, but follow-up observations by other teams never quite confirmed it with complete certainty. The signal was always at the edge of detection limits. The uncertainty margins always overlapped with zero. By 2010, nobody was publishing papers about Tau Ceti's planet anymore. Today, if you search the NASA Exoplanet Archive, you will find a note that the detection status is uncertain. Marcy himself moved on to other research programs. He did not retire, but he did not continue pursuing this particular planet. It simply stopped being part of his portfolio. And yet in 1998, the same astronomers who discovered 51 Pegasi b, the same people who had just shown the world that exoplanets were common, had believed in this planet enough to stake their professional reputation on its existence. There is another dimension to these lost planets that institutional pressure created. The funding landscape for exoplanet research in the late 1990s and early 2000s was intensely competitive. Whoever made the most discoveries received the most grant money. Whoever published the most papers in prestigious journals received the most invitations to conferences, the most faculty positions, the most professional recognition. The temptation to announce discoveries that were probable but not completely certain was real. The pressure to move forward to the next detection rather than spend years confirming the previous one was institutional and relentless. A scientist who spent 4 years carefully confirming a single marginal detection was a scientist whose citation count was stagnating while competitors were discovering new planets monthly. This is not to say that the early exoplanet discoverers were dishonest. They were working within a system that rewarded speed and volume over certainty. The system itself created the conditions for discoveries that could not be maintained. But there is a specific contradiction that the official history of exoplanet astronomy has never adequately addressed. The discovery of these marginal planets, the ones that were eventually lost to follow-up observation, directly triggered the funding that made possible the space-based instruments, particularly the Kepler Space Telescope, that would eventually discover more than 2,500 confirmed exoplanets with high certainty. If the early exoplanet discoveries had been fewer and more cautious, if the initial excitement had been dampened by institutional skepticism, the political will to fund a billion-dollar space telescope might never have existed. The lost planets were not a waste. They were the hype that created the infrastructure that made real exoplanet astronomy possible. This is the part of the story that nobody tells. The marginal detections, the candidates that faded away, the planets that were lost, were the necessary sacrifices to the political machinery that eventually legitimized the field. The question that has haunted exoplanet astronomy ever since is simple but has never been fully answered. How many of the lost planets were actually real? How many were genuine planetary detections that simply fell through the cracks of observational follow-up and institutional memory? How many were instrumental noise or misanalyzed data? The answer is that nobody knows. The data files still exist in some cases. The original observations can in principle be reanalyzed with modern computational methods. But reanalysis is not fashionable work. It does not produce citations. It does not generate new discoveries. It does not advance careers, so the lost planets remain lost, not because we lack the ability to investigate them, but because the incentive structure of modern astronomy does not reward investigating them. There is one specific example that illustrates this perfectly, and that has only recently come to light. In 1999, a team at the Steward Observatory in Arizona announced the discovery of a planet around the star Epsilon Eridani. The planet had a long orbital period and a high eccentricity. The detection was published and announced. The planet was included in exoplanet databases. But within a few years, new radial velocity measurements began to suggest that the signal might not be a single planet, but rather two planets, with orbits that happened to create a pattern that mimicked a single long-period planet. The original discoverers did not pursue this alternative hypothesis seriously. Other teams did not pursue it either. The question hung in the air. In 2019, more than 2 decades later, a team reanalyzing archival radial velocity data found strong evidence that Epsilon Eridani's signal was indeed 2 planets, not 1. But this reanalysis was published in an obscure journal and was barely cited. The original false detection and the eventual true detection both appear in the historical record, creating confusion rather than clarity about what was actually found. There is another curious aspect to the lost planets that connects to our present moment. The data archives, where the original observations are stored, are now vulnerable to digital obsolescence. The format that was standard in 2000 is not easily accessible now, in 2026. The researchers who could interpret the raw observational files have retired or died. The institutional knowledge required to understand how the instruments were calibrated has vanished. There is a genuine risk that within another decade or two, the raw data from the first exoplanet discoveries will become inaccessible to future scientists. The lost planets might not just be forgotten. They might become literally unrecoverable, even if future astronomers become desperately interested in revisiting the question. The current state of knowledge about these lost planets is that they exist in a kind of scientific purgatory. They are acknowledged to exist by specialists in the history of exoplanet astronomy, but they are treated as cautionary tales rather than as legitimate objects of study. The planets that were probably real but never confirmed sit in databases marked as candidates rather than confirmed detections. The planets that were almost certainly false positives have been quietly removed from most popular exoplanet catalogues, though traces of them remain in comprehensive databases. The planets that might have been real, but for which the ambiguity will never be resolved, are simply forgotten, their names appearing in old papers that fewer and fewer astronomers read. What all of this reveals is something uncomfortable about how science actually works at the frontier. The official narrative is that science is self-correcting, that bad data gets weeded out, that the community eventually converges on truth. This is accurate in the long term, but in the medium term, which can last decades, science is also a process of collective amnesia, institutional power dynamics, funding constraints, and the brutal truth that confirming an old, uncertain detection is far less rewarding than making a new discovery. The lost planets are not an anomaly. They are a feature of how scientific progress actually happens. For every discovery that gets sustained attention, there are dozens that get marginally documented and then forgotten, not because they are false, but because the incentives point elsewhere. The specific planets that form this lost archive have names that appear rarely in modern scientific literature, Tau Ceti b, the marginal detection from 1998, the candidate planets around Gliese 667, discovered with great confidence but never independently confirmed. The signal around HD 8551 that some astronomers insisted was a planet and others insisted was a stellar activity pattern that coincidentally mimicked planetary motion. The detection around Alpha Centauri b that was announced in 2016 but retracted in 2020 after reanalysis suggested instrumental artifacts. The planet around Proxima Centauri b that caused a minor controversy about whether the discovery had been robust enough for announcement, a controversy that was never fully resolved. These names exist in the archaeological layer of exoplanet astronomy, like the footprints of creatures that no longer appear in contemporary ecology textbooks. But here is what connects the lost planets to today in a way that matters. The methods developed to search for exoplanets that were lost to follow-up observation have become the foundational techniques for searching for biosignatures in exoplanet atmospheres. The spectroscopic methods, the statistical frameworks for distinguishing signal from noise, the follow-up observation protocols, all of these were refined in the fires of discovering and then losing planets in the late 20th century. The researchers who made those marginal detections and whose work faded away contributed to a scientific infrastructure that is right now, in 2026, being pointed at planets like K2-18b and TRAPPIST-1e in the search for signs of life. The lost planets might not be remembered, but the methods created in the desperate chase to find them are the very tools that are opening the era of exoplanet characterization. The dead ends of exoplanet discovery became the foundations of exoplanet astronomy. The forgotten detections created the framework for future discoveries that will not be forgotten. That is the final twist in this story. The planets that science lost track of did not disappear without consequence. They shaped everything that came after.